Okay. So today I want to do Banach Algebras. So possibly I have defined it earlier. I don't know. So the definition. Okay. So as I said, these things you can find in the Sundar's book Spectral Theory. Okay. Maybe not all details, but the basic whatever I'm going to do, it's there. Okay. So the definition of a Banach algebra is we usually have this notation script A for a Banach algebra is a Banach algebra. So which is an algebra. Okay, so it's an algebra that is a ring. It has a product which is associative product. Okay, so it's a ring and vector space. Okay, which is an algebra. So we have an associative product which is also distributive with respect to the addition. So we have an addition operation, we have a multiplication operation, and this multiplication operation and the addition operation they are they are related by the distributive law. So then we have a norm on this, and it's also a Banach space. Okay, and we know that when we have a norm, then the addition operation, scalar multiplication, they are all continuous with respect to norm. That follows from the properties of norm. Further, we want the multiplication operation is also continuous. So whatever it means is it's a Banach space satisfying. It's an algebra. It's a Banach space, and the product satisfies the following: satisfying. This is the Banach algebra condition. Norm xy is less than or equal to norm x times norm y. Okay? This makes the multiplication operation continuous. So it's actually joint continuous. It's maybe I will leave it as an exercise. Okay, this is an assignment. Okay, assignment. Show multiplication. I think the proof is there in the book. Maybe you can copy. I don't mind. Multiplication is jointly continuous. Okay, it's the same thing. It's just we just write the multiplication and show that. It's an epsilon argument. That's jointly continuous. Okay, with respect to norm. Okay. So this is what a Banach algebra. So a Banach algebra is an algebra which is also a Banach space, and the product satisfies this condition. Norm xy is less than or equal to norm x times norm y for all script A. So examples, we will be dealing with only two examples. One is B of h or any norm closed algebra of B of h. Okay, that's what we will deal with. We will basically be dealing with B of h because we want to prove spectral theorem. So that's what we will be dealing with. You can, or otherwise you can take a subalgebra of B of h and take the closure. So it's a norm closed subalgebra of B of h. That's what we will be dealing with. A special case is C of x. But C of x is actually can be represented as a norm closed subalgebra of B of h. Okay, you have C of x. This is a Banach, this is with respect to usual product, pointwise product. Pointwise product and the usual norm, the infinity norm. This is a Banach algebra, which you can easily see. But then this is one of those cases. C of x can be represented inside B of L2 x with respect to some measure, any measure you want. You take some regular measure, something. If it is x is a compact metric space, then you can have a regular measure. So you take a finite measure, that's not necessary, but you can take a finite measure, for example. Okay. Then as multiplication operator, f going to mf. Okay. Here mf at g at x equal to f of x g of x. This multiplication, we discussed this multiplication operator in the last course, and that's a representation of this. So it's a faithful representation of this, and the norms will be preserved. The norm, infinity norm, is exactly same as the operator norm there. Okay, that also we have proved. So because of that, you can consider C of x as operator, actually as a norm closed subalgebra of operators on L2x. Okay, so this is a Banach algebra. Okay, it's in fact a C-star algebra. What we are going to discuss is our C-star algebras. So these are all examples of Banach algebra, which are actually operator algebras, which are subset of, which are subalgebras of B of h. So there is something which is not, which will not a C-star algebra. I mean, this will be, we will further have a star operation. We will call it a C-star algebra. We will come to that. But there is a non-example. I mean, it's a Banach algebra, but it's not a C-star algebra. You take L1 of X with respect to convolution. Okay, we will not be discussing this. This is just a example. Okay, we have discussed convolution in the last course, the previous course. And with respect to this convolution, it's a Banach algebra. But that doesn't satisfy. I mean, you can have the inverse operation as a star operation. That it will not satisfy the C-star identity, which we will be defining soon. Okay, so this is a Banach algebra. Okay, but not a C-star algebra with respect to the inverse operation. Or I mean, you have to define a star with respect to that. It will not be a Banach C-star algebra. Anyway, we are not going to discuss that. So this is another example. Okay. So, but we will be dealing with B of H and subalgebras of B of H. That's what we will be dealing. Okay. So the nice thing about the Banach algebra is, this is a remark. We have already seen multiplication operators on L2. We can define a multiplication operator. This is the non-commutative multiplication. I mean, the Lx and Ly will not commute. So for so A is a Banach algebra always. For X in A, you can define Lx, which is an operator from A to A. This is A is a Banach space, so it's an operator from A to A, where Y going to xy. You can but L is for left. Okay, you can similarly define right operation. Okay, X. Oh, sorry, again I am writing X. Y going to xy. So this will be a representation. I mean, this is a then Lx is bounded. So, and further, I want to say that our Banach algebra, we will always assume it's unital. Okay, usually the Banach algebra theory, it need not be unital, but we will assume that it's unital. Okay, so our assumption, I will write here because always assume there exists one in A, which is identity. Okay, identity satisfies the property of the ring. I mean, you know the identity in the ring. Okay, 1x times x1 equal to x. Okay, it will satisfy that. So Lx is an operator from A to A, y going to xy. Then you know norm xy, Lx acting on any y equal to norm xy is less than or equal to norm x times norm y. So Lx is norm Lx is less than or equal to 1. But then at the identity, it is equal to x. So Lx of 1 equal to x itself. So this implies norm Lx equal to 1. Okay. Similarly, you can define right multiplication, but you need to take the point is x going to Lx is an representation. It's called regular representation. Lx is a representation. That is, I mean, to satisfy this property, Lxy equal to Lx times Ly, the operator multiplication. And these things will imply that Lx inverse is equal to Lx inverse. So Lx is a invertible. I mean, it's a continuous and it's also invertible, and the inverse is also continuous. Okay, so Lx is a homeomorphism. I mean, it's a not just it's an isomorphism. Okay? If it is invertible, I mean, if
shouldn't normal x be norm of x? Normal x should be norm of x, right?
it is norm of x. I'm sorry. Yeah, it's not one. Sorry, it's norm of x. Sure. So it's a representation and it's equal to norm of x. Correct. It's not one. I mean, it's norm of x. Correct. So Lx inverse equal to Lx inverse if x is invertible. If as a ring element, if x is invertible, then Lx inverse is Lx inverse. That is clear because the x going to Lx is a representation. It's clear that when you multiply Lx, it's going to be xy. When you apply Ly, it's going to be, first Ly, then Lx means it is multiplication by Lxy. So it's equal to Lxy. And Lx x inverse is Lx inverse of the Lx. So Lx is invertible, then x is invertible. Okay. Okay, so this is a isomorphism. Lx is an isomorphism, then x is invertible. And since we have identity, okay, so now I want to prove something really nice about this proposition. So A is a Banach algebra. Sometime I may not mention, it's always a Banach algebra. Okay. X is in A such that one norm of 1 minus x is less than 1. Okay. Then x is invertible. Indeed, the x inverse, we can write it, which is n equal to 0 to infinity, 1 minus 1 minus x power n. So proof is direct. So the series summation n equal to 0 to 1 minus x power n is less than infinity. Okay. This is a geometric series. So since 1 minus x is less than 1, okay, this exists. So since this is a Banach space, since A is a Banach space, summation n equal to 0 to infinity, 1 minus x power n exists. Okay, the sum converges. Okay. So suppose this is equal to yes, then we have, suppose we call suppose Sn is the partial sum, okay, and this is equal to S. Okay, let it be S, and Sn is the partial sum. Then we have Sn times 1 minus x equal to 1 minus x times Sn. Okay, this is equal to, when you multiply by 1 minus x, the first term, it's a first term is identity. N equal to 0, it's identity. Okay, with 1 minus x power 0 equal to identity 1. So the first term gets multiplied by 1. Everything is increased by 1 power 1. So this is going to be Sn plus 1, Sn plus 1, no? Whatever. Sn plus 1 minus 1. Right? So take n goes to infinity. This implies s into 1 minus x equal to 1 minus x into s equal to s minus 1. So if you just multiply and cancel it, if you cancel it, this implies xs equal to sx equal to 1. So that's what we want to prove. Okay, the sum, whatever the sum we have defined, that's the inverse of this. That's what we wanted to do. So the x inverse looks like this. Okay, so if we have any element in the C-star algebra, which is at a distance of 1, from the identity, then they are all invertible. Okay, so that's an open ball around the identity, which are open ball of radius 1, which is invertible. Which are all invertible. Okay. So from this, we want to prove the following. The next proposition: you take lambda in C and x in A, and mod lambda is greater than norm x. Okay. Then x minus lambda is invertible. As you can see, this has something to do with the spectrum and other things. Okay, so that's why we are considering this. So x minus lambda is invertible, and x minus lambda inverse equal to minus of x power n lambda power n plus 1, n equal to 0 to infinity. Okay. So if we have lambda, a scalar lambda, a complex number scalar lambda, is that lambda is greater than norm x, then x minus lambda is invertible. And the inverse is actually given by this. Okay, so we have the following. We have lambda minus, sorry, we have that norm x by mod lambda is less than 1. Okay. Okay. So this implies 1 minus x by lambda is invertible. Right. Now we want to, I formally write it, x minus lambda inverse has to look like 1 minus 1 minus x by lambda inverse, right? Times lambda times 1 by lambda, right? times 1 by lambda. 1 by lambda or lambda. I should get a lambda power n plus 1 in the bottom. So this should be 1 by, let me see, 1 by lambda into 1 minus x by lambda, right? So what is this? This is, it's get multiplied by lambda, no? There is some, let me just write this sum, okay? So it will be clear. This sum is minus summation n equal to 0 to infinity x power n by lambda power n. I take the 1 by lambda out. So this is equal to, because mod x by, I mean, norm x by mod lambda is less than or equal to 1. So this is equal to minus 1 by lambda, 1 minus x by lambda inverse, right? That's the inverse. Okay, that's inverse. So this is equal to x minus lambda inverse. That's what I want to say. Because I'm taking inverse. So if you you take this lambda here, I mean, you multiply the lambda here, you will get that, right? X minus lambda inverse. Is this okay? I mean, you can take the minus inverse. I mean, if you take the inverse of minus x is minus x inverse, okay, and you can take the 1 by lambda, and when you take, I mean, when you invert something, the 1 by lambda, you will get the 1 by lambda, right? Lambda times is okay, no? This is okay. I'm saying that x minus lambda into 1 by lambda, okay, inverse is equal to inverse of this. No, sorry, lambda.
This is okay.
This is okay. You just take the inverse.
Yeah.
You will be, it's anyway commutative. It's just scalar. It is just the product of the inverses, and it is just that, right? Yeah. So this is okay. So if it's okay for everyone, I believe. Otherwise, you just get convinced. Okay. Okay. So this is okay. So this is the inverse. Okay. Okay. So next, I want to prove that the inverse map is a continuous map. Okay. So these are the two things we have proved. If norm x 1 minus 6, norm of 1 minus 6 is less than 1, then it is invertible. And if scalar lambda, mod lambda is greater than norm x, then x minus lambda is invertible. The third thing we want to prove is this is proposition. So let's make a notation. G of A is all invertible elements. Okay. Elements in A. Okay. Then the proposition. Of course, this is a bijection anyway. Is a homeomorphism. Okay. It's a homeomorphism onto G of A. So this is, I mean, we just have to prove that it's a if the map is continuous. If we only have to, I mean, it's clear it's a bijection. We only have to prove that the map is continuous. Okay. That is, if x, if some x, I mean, if it's a Banach space. So if xn converges to y, I mean, xn converges to x, then we have to prove that xn inverse converges to x inverse. So, I mean, if some x converges to y, some x is close to y, then x inverse should be close to y inverse. That's what we want to prove, as close as y. So we want to consider this x minus y, and x minus y is equal to x inverse into 1 minus x inverse y, right? X inverse y. Okay. And so I want to consider this. Okay. So 1 minus, so I want to consider 1 minus x inverse y. So for that I have to consider the norm of x inverse y. Okay. This is less than or equal to norm x inverse times norm y. Okay. So if norm y is less than 1 by norm x inverse, okay, I mean fix x, okay, fix x in A. We want to prove that the map, I mean, when y is close to x, then y inverse is close to x inverse. That's what we want to prove. We want to prove the continuity of this map.
So
Continuity.
in the first line, like x minus y is x times 1 minus x inverse y.
X in, yes, sorry, correct. X times, correct. Yeah, correct. Yeah. So anyway, I want to get this. The other thing is okay. Yeah, that's right. Thanks. Okay. Now just if norm y is less than 1 by norm x inverse, then norm x inverse y is less than 1. So if this is less than 1. So I mean, if this, I'm just saying, I mean, this is just I mean, x is fixed, so 1 by x inverse is some constant. And if we take the norm y very close to 0, I mean, close to 0 means less than epsilon. So in particular, it will be, you can take it less than 1 by x inverse. Okay. So then x inverse y is, I mean, when y is close to x, then norm of x inverse y is less than 1. Okay, that's what I want to say. So then 1 minus x inverse y. So x in not, I mean, let's not fix x in g of a. We fix x in g of a. So we fix x in invertible element x, then 1 minus norm x inverse. This is invertible. This is invertible by the earlier proposition. Okay. So, and if you have, I mean, if you have two elements which are in the product is, I mean, this set of all invertible elements, this G of A is closed under products. Okay. I mean, the product of the inverse of xy is y inverse x inverse. You know that. So because of that, the x times that is also invertible. Okay, x times 1 minus x inverse y, x minus y equal to this. Okay, equal to this, and this is equal to x times, and so this is summation n equal to 0 to infinity x inverse y power n, right? Right. So this is x minus 1, right? Okay. Now what do you want to do? I want to consider this x minus y. No, I'm sorry. X minus y inverse equal to I want to consider the inverse equal to x inverse. Okay. And which is equal to the inverse is in this side or that side. I think this is okay, no? X minus y equal to 1 minus x inverse y. So the inverse should be on this side. I may make mistake. Please correct me if I am wrong anywhere. So
and now this is fine.
The idea is fine. So the idea is you have to consider this x minus y inverse equal to 1 minus x inverse y x inverse. So which is equal to this, right? Now we want to consider this, okay, to prove that here this should be x inverse. Okay. Now we want to consider this. We want to prove this goes to 0 as y goes to 0. That's what we want to do, right? Correct? This is what we want to do. Then we prove the continuity of the inverse. If y goes to 0, then this my x minus y will go to x. Okay, I mean that's just addition is continuous. The x minus will go to x. Then x minus y inverse should go to x. I mean this x minus this just means that x minus y inverse will go to x inverse. So that is what continuity means. Correct? Okay. So this is what we want to prove. But then that we can, so, but then we know we have already written what is x minus y inverse. So norm x minus y inverse minus x inverse using that summation. The summation will start from 1, that's all. Summation will start from n equal to 1 to infinity. Okay? X inverse y power n x inverse, right? That's what x minus y inverse minus x inverse. At n equal to 0, it is just x inverse. This will become identity. Sorry, this power is n is outside. Okay. Right? Okay. Now this goes to 0 as norm y goes to 0. This is because it starts from, I mean, you just want to compute the norm anyway. Okay. And that is less than or equal to norm x inverse norm x inverse times summation n equal to 1 to infinity norm y power n norm x inverse power n, right? Okay. So which is equal to norm x inverse is just a geometric series. So the first term is norm y times norm x inverse power n 1 minus, and the product is also norm y times norm x inverse, which goes to, and this goes to 0, this goes to 0. I mean, this, the denominator goes to 1, so this goes to 0 as norm y goes to 0. I mean, y goes to 0 and norm y goes to 0, both are same. Okay? So that's what we want. Okay? Maybe I will discuss again. We want to prove that x goes to x inverse is continuous. So to prove that, it is enough to prove this statement, this, right? This goes to 0. That's what we want to prove. Okay? This goes to 0 is what, I mean, we want to prove that the map x goes to x inverse goes to 0. I mean, x going to x inverse is continuous. To prove that, it is enough to prove that this goes to 0. Okay? I mean, x plus y or x minus y, doesn't matter. Okay? X plus x plus y goes to x. That's what we want to prove. As y goes to 0. Okay? So that is what is being proved by all these inequalities. Is fine. If anybody has a problem, I will go through this. There is really nothing. It is just it looks messy. That's why I get confused, but it's direct. The proof is direct. Okay.
Yeah,
So,
it's
Why
fine.
is there the power?
say it again.
Like, why is there a power n in the last line? Like norm y times norm x inverse power n.
Yeah, in the last line. Oh, there is no power. There is no power. That was mistake. Sorry. I don't intend to write it. Yeah. There is no power. It's just a geometric series. The sum is first term a by 1 minus r or something. So that's what I wrote. Okay. The a is also the formula, geometric series formula, a by 1 minus r. A is also norm y times norm x inverse. R is also norm y norm. That's what I have written, and that goes to 0. Okay. Okay. There is no power n. Okay. Now we want to prove that the set of all invertible elements is open. Okay. The next proposition. G of A is open. So to prove open, you have to prove that all points are interior points. So clearly 1 is an interior point, okay? Because there is we have a radius. So clearly 1 is an interior point. 1 is one element of G of A is an interior point. Since there is I mean, 1 minus x is less than, I mean, maybe I'll write it in terms of open balls. since B of 1, 1 is contained in G of A. This one is identity, the other one is number 1, real number 1. So B11 is contained in, maybe I'll write it like this, and this is, that one is 1. So 1 is an interior point. But then we know that this Lx from G of A to G of A is a homeomorphism. For all x in G of A. Right? I mean, it's a homeomorphism. First, it's a homeomorphism, clearly. I mean, it's already a 1-1 map, but it's when you restrict the inverse is continuous and all that. So it's a homeomorphism. So it takes any open set around 1 to a open set around x, which is contained in G of A. You have an open set around 1. Okay, take a open set around 1. It will take Lx will take it to a open set around x. Okay, which is still contained in G of A because it's a homeomorphism from G of A to G of A. Okay? So this makes x is an interior. Okay, because it's a homeomorphism. Lx takes 1 to x because of that. Okay, this is fine. Okay, so
yeah,
this is done. Okay, so what is next? Next, I want to define the spectrum. Okay. Okay. So definition: the spectrum, which we denote by sigma of x for x in A. You take a Banach algebra element A, then the spectrum sigma x is defined to be all those lambda in C, which you must have seen it in linear algebra course, all lambda in C such that x minus lambda is not invertible. Not invertible. Okay, if it is invertible, that's called what is called resolvent, which is denoted by rho of x and which is equal to C minus sigma. It's just the complement. Okay, rho of x is just the complement. It's all those lambda such that x minus lambda is invertible. So first we know that since we know that we have proved that if a scalar lambda is greater than norm x, then it is invertible. X minus lambda is invertible. So this implies that sigma x is contained in B of 0 times norm x. I mean, which is in C. Okay? Sigma x is a subset of C, complex plane, and it is contained in there. So sigma x is bounded. Okay, and rho x is, this is just defined. I mean, since rho x is, the addition map is continuous and all that, so rho x is open in C. Okay? So this implies sigma x is closed. So sigma x is compact. It's a closed and bounded, so sigma x is compact. Compact subset of.
so by B0 norm x, you mean the closed ball?
Yeah. It is contained. It's a closed ball. Yeah. Maybe you
Because for invertibility,
you have to take. Usually x will norm x will be there. It is in fact that we have proved for compact operation. We haven't proved. We haven't completely proved. Anyway, I will come to that. So yeah, you are right. It's a closed ball. Or you have to take, it's a closed ball. Correct. Okay, so sigma x is compact. You are right. Now, because mostly norm, not when x is normal, norm x will be there. Okay, so because of that, this is you have to take closed ball. Correct. So sigma x is compact. Right. Okay, so then we want to prove sigma x is actually non-empty. Okay, sigma x is bounded, which is clear. Sigma x is closed because the complement is open, and so it's compact. We want to prove it's actually non-empty. To prove that, we need something.
So how is the complement open? Rho x.
Rho x is open because the set of all invertible elements are open, and it is just all those I mean, what is that? It's a, why is it open? X minus, it is just, you have a X here. I mean, it is just, you have a map from C, C to, what is that? C to A. You have a map, lambda going to X minus, right? And this is just the rho of X is just the inverse image. This map is continuous map, of course. To call this map continuous, what is this map you want to call? Phi or something. Then this is just phi inverse of G of A, okay, which is O. Phi is continuous.
Yeah. Okay.
So continuous image of, okay, that's all. Okay. Okay. So we want to prove it's non-empty. To prove that, we want to define something called resolvent function, which we will not be using anymore, only for this proposition. Rx lambda is just X minus lambda inverse for lambda in rho of X. Okay? When lambda is in the resolvent, we define Rx lambda is it's a function from rho of X, lambda going to A, which is X minus lambda inverse. Okay. This is what is called a resolvent function, which is useful elsewhere, but we will not be discussing this in this course. We will be using only for this particular proposition. Okay. So first thing is, so yeah, norm Rx lambda goes to 0, then the resolvent equation, then weakly analytic. So limit mod lambda goes to infinity, norm of Rx lambda equal to 0. That's one thing. The second thing is lambda minus mu Rx lambda Rx mu, okay, equal to Rx lambda minus Rx mu, okay, for all lambda mu in the result. Okay. That's okay. Third one is the map lambda going to Rx lambda is weakly analytic. That is, for all phi in A star, A is a Banach space. So you take a linear functional on continuous linear functional on A, phi is the dual of A, then phi of Rx lambda, lambda going to this is analytic. It's a complex valued function, so it is analytic. It's analytic. And it's also true that doesn't mean it follows from the first condition, and limit mod lambda goes to infinity, then phi of Rx lambda. Because it's complex number, you can just write it. We won't need now. Goes to 0. Okay. Phi of Rx lambda goes to 0. Okay, these are the three things we want to prove. I wanted to write proof, but I was writing something else. Okay, so the first thing is clear. Because Rx lambda, which is just X minus lambda inverse, that is equal to summation n equal to 0 to infinity minus x power. We want to talk about the norm. This is norm equal to, is less than or equal to is less than or equal to norm x power n plus 1. There is no infinity. Okay. And that is equal to, the first term is when n equal to 0, which is just 1 by lambda, 1 by lambda. right? And then 1 by 1 minus norm x by norm lambda. Okay, so which will become, which is equal to, so this is just norm lambda, mod lambda, which is equal to 1 by mod lambda into mod lambda minus norm x. That will go away. This lambda will go away, which goes to 0. Okay, it's fine. Okay, this is 1. 2, and we just used our formula for x minus lambda inverse. Okay. Okay. The second one is also direct, which just says the following. We want to talk about lambda minus mu Rx lambda Rx mu, which is equal to x minus mu minus x minus lambda, right, to Rx lambda Rx mu. And Rx lambda is just x minus lambda inverse. So if you multiply, that will go away, but Rx, so which is just Rx lambda. Rx mu, if you, I mean, Rx lambda and Rx mu commute, okay? I mean, it is just x minus lambda and x minus mu commutes because it differs by a scalar only. So they commute, and you can if you multiply this, you will get Rx lambda. Rx mu will get killed, and if you multiply this, Rx mu will get killed, and Rx lambda will get killed, and Rx mu. So that's what it is. So this is clear. Okay. Then the third one, we want to prove that it's analytic. So phi x, we want to talk about phi of Rx lambda. So we want to consider this function lambda going to Rx lambda, phi of Rx lambda. Okay, for phi in A star. We want to prove that the map lambda going to Rx lambda is analytic. That's what we want to prove. Okay, so we consider this lambda going to phi of Rx lambda. So we want to compute its derivative. So that's why we have this resolvent equation. So that equation we have. So we want to consider this when lambda not equal to mu, Rx lambda, Rx mu, okay, phi of this divided by lambda minus mu. But then this is same as the other one, lambda minus mu into phi of Rx lambda times phi of Rx mu. If you, so it's just in the product. Phi of Rx lambda times Rx mu. Okay. But then Rx lambda, I mean, so we have proved that the inverse map is continuous. So as lambda goes to mu or mu goes to lambda, whatever, maybe mu goes to lambda, we fix lambda, mu goes to lambda. I mean, it's clear that x minus mu goes to x minus lambda. So this implies x minus mu inverse goes to x minus lambda inverse. So Rx mu will go to Rx lambda. So this whole thing, whatever, this will go to phi of Rx lambda square, right? I mean, times 0.
So the lambda minus mu gets cancelled.
There is no lambda minus. Sorry.
Yeah.
That's what I'm wondering why I am getting 0. Yeah. This is equal to phi of Rx lambda minus mu. So the limit exists. Okay, that's what we want to do. So lambda going to phi x of Rx, phi of Rx lambda is analytic, is differentiable, so it's analytic as a complex function. Okay. So that's what we want to do. And it's clear limit lambda mod lambda goes to infinity, phi of Rx lambda goes to equal to 0. I mean, since we know that, I mean, for the first part is Rx lambda goes to 0. Norm of Rx lambda go to 0. So this is just less than, this is less than or equal to, mod of this is less than or equal to norm phi times norm of Rx lambda. Okay, so that goes to 0, so this goes to 0. Okay, so the first part is also proved. Okay, now we prove the following proposition, or maybe corollary to all those things. Sigma x is non-empty. We have already proved it's compact, so it's non-empty. Proof. Suppose empty, that is rho of x is equal to c. Okay, then lambda going to phi of Rx lambda is an entire function. Entire function for phi, any phi in A star, for any fixed phi in A star. Okay, for phi in maybe for all, we'll get, I mean, phi is arbitrary anyway. So for phi in A star, okay, it's an entire function, but phi of Rx lambda, this goes to 0 as lambda goes to infinity. Okay, so it's bounded. Okay, so this implies this function is bounded. Is bounded. So a bounded entire function is constant, but since the limit goes to 0 in the infinity, so it has to be equal to 0. So it's called Liouville's theorem. I hope all of you know this theorem. Okay, imply that phi of Rx lambda equals 0. This is for all phi in A star. Okay. This implies Rx lambda equals 0 because phi separates points. Okay, since A star separates points, A star separates. So, but Rx lambda is invertible, so it cannot be equal to 0. Okay, so this is not possible. So, from what we have done in the earlier proposition and Liouville's theorem, imply that Rx lambda, I mean, sigma x is non-empty. So, if it is empty, then this whatever the function we have is an entire function. But from whatever we have done, the calculation we have done, it is a bounded entire function whose limit vanishes at infinity. So it has to be 0, but that's not possible because it's invertible. Rx lambda is invertible. So this is not possible. Okay. So I think it's fine.
Yeah, this is fine.
Okay, this is fine. So what else I'm left with? Yeah, I have to prove spectral mapping theorem and then stop here. What is spectral mapping theorem? This is for any Banach algebra. So, oops. Yeah, this is what is called spectral mapping theorem. There are different versions of this spectral mapping theorem. This is spectral mapping theorem by Banach algebras. Okay. Okay. You can have for continuous function also, but for polynomials, we will be proving this. Okay. So let P be a polynomial. Small p is a polynomial. It's a with complex coefficient. Okay. Coefficients. Okay. Then a polynomial is a, I mean, if, of course, suppose let P of Z equal to summation AI Z power n. Okay, n equal to 0 to some n, capital N. So this is how the polynomial looks. Then define P of x for x in A. You can define, if you have a polynomial, then you can define, just substitute instead of Z. If you have any element x, then you can talk about x power n. Okay, so you can define P of x equal to summation n equal to 0 to n. ai x power n. You can talk about this. This is also an element in A.
an, not I.
Hmm?
It should be an.
Okay. Okay. Yeah. An x power n. So this is just a polynomial, and this map P going to P of x is a homomorphism. From the ring of from all polynomials will to A. That is just clear. If you have the product, then the same. It's all. This is just a commutative thing. If you because it involves only the element x, the powers of x, and they all commute, so it's commutative. So because of that, it's a homomorphism. This is clear. Okay? I hope it's clear. The second thing is what is called the spectral mapping. This is the second part is what is called spectral mapping theorem. So for all x in A, we can consider sigma of P of x. Okay, how is it related to the sigma of x? So which is just P of sigma of x. What is P of sigma of x? It is just all those P of lambda in sigma of x. You just take the P of lambda, value of all P of lambda with lambda in sigma of x. Then that is what is P of sigma of x. So sigma of P of x equal to P of sigma of x. Okay, so this is what is called spectral mapping theory. So proof. So only two we have to prove. The one is clear. The homomorphism part is clear. You just have to write it and it will just practice. Okay. So why is this true? So assume P of z equal to summation n equal to 0 to n an z power n with an not equal to 0. Okay, so we can assume. And that so it's a polynomial with complex coefficient, and complex numbers are algebraically closed. So there exists lambda 1 up to it's a n degree polynomial. So lambda, maybe they are repeating lambda n such that P of lambda P of x P of x P of z P of z minus lambda. So for any lambda in C, any lambda in C, this is true. P of z minus lambda. It looks like some. This is just the product. Product. This is notation for product. Okay, I equal to 1 to n, because it's a power n. It will have n roots. So I equal to power n an times z minus lambda. I'm just writing factorizing it. That's all. Okay, it just there exists a factorization because it's a complex field. It's over complex field. Okay, so because of that. So if we take any lambda in C, then this is true. Because an is not equal to 0, you can take the an out and you can write it like this. Okay. Now suppose if lambda is in, we want to prove that sigma of px is equal to p of sigma of x. That's what we want to prove. It's enough to prove rho of p of x equal to p of rho of x. Okay, the complements. Enough to prove this for complements. Okay, so if lambda is in rho of p of x, one is rho, the other one is p. Okay, p of rho of x equal to rho. I will write it neatly. So enough to prove p of, this is rho of x. Rho is the resolvent, which is rho of p of x. Okay, so lambda is in rho of p of x. which is equivalent to saying, lambda is in row of P of X means the left-hand side does not vanish. Okay, lambda is not equal to lambda is in, this is equal to, lambda is in row of P of X means P of X minus lambda is not invertible, which is equivalent to saying P of X minus lambda is not invertible. That's what it means. That's the meaning of this. I'm claiming that that is equivalent to saying P of, Now this P of X minus lambda is a product of some n elements in A. Okay? And in any ring, the product of n commuting elements is invertible if and only if each one is invertible. It is just easy. Okay? So this
Px minus lambda is invertible, right?
This is invertible. Sorry.
Yeah.
If it is invertible. Is invertible. That is equivalent to saying x minus lambda I is invertible for all n. If you have n element x1 up to xn in a ring, the product and commuting, they are all commuting because they differ by a scalar only. They are all commuting. Then the product is invertible if and only if each one of them is invertible. That is clear. If the product is invertible, then you can take the you can write the inverse of something as you take the product of rest of them and just multiply the inverse. You will get the inverse element of each of them. And if each one of them invertible, then you can reverse the product, and then it does not matter because it's commutative. So they are all commuting. So you can just take then you take the inverse of each one of them, product of the inverse, that will give you the product. So it's clear. So because of that, x minus lambda is invertible. Okay. So each x minus lambda are invertible. Okay. So this is equivalent to saying lambda is in P of rho of x. P of, that's what we want. P of x. P of x. Right? Then the product is also invertible. So right? This just means that P of x minus lambda is invertible. P of x, sorry. X minus P of lambda is invertible. X minus P of lambda minus x is invertible. Each x minus lambda is invertible. And this just means that P of rho of x, so which is just P of
So each of these lambdas are invertible.
each of lambdas are invertible.
So P of lambda is equal to lambda. So that means that lambda is in P of
Lambda
X.
equal to lambda. What are you saying?
P of lambda is equals to lambda, because if we substitute in the polynomial equation,
Yeah.
then we get that P of lambda is equal to lambda.
Yeah, P of lambda. Yeah, P of lambda equal to lambda.
Yeah. So and lambda belongs to rho of x. So lambda.
What do you mean? Yeah, exactly, correct. Yeah, if it vanishes, then P of lambda equal to lambda. Is that what you are saying?
Yeah.
So then that is not clear. So that's correct. This is fine with everyone. So this is what I want to do today. I have a lot of time. I have 15 minutes more, but it's fine. I want to start something else tomorrow. In the next class. Okay. So it's fine. Any questions?
Sir?
Yeah.
Sir, can every non-empty compact subset of C be the spectrum of some element of a Banach algebra?
Yeah, I think so. You can
Like,
write.
how do you come up with such an element? I mean, whose spectrum is a given non-empty compact subset of
Theory, I believe. Let's see. Let's see in the end. You ask this question in the end. Okay. Let's see. Okay. When we discuss spectral theorem, we will talk about this question. You remember to ask this question. Okay.
Okay, sir.
Okay.